Hello everyone, welcome to the IMS GATE Academy. I hope you are all good and your preparation going to in a right direction. I am Pragyabrat Tripathi. So with the discussion, continuity of the discussion of the subject thermodynamics, right? So what up to that, what we will cover, what we already covered, that we understand the what is the system surrounding all the things and what is the reversible work, what is the quasi-static process, what is the flow work, what is the difference between flow work and quasi-static work or a thermodynamic work. Okay, so one thing is very clear that the thermodynamic work or a quasi-static work must be internal reversible. That means, see, this is the reversible. Okay, but quasi-static must be a reversible process, must be a quasi-static process, but quasi-static process need not be a reversible. Why? Because there may be external irreversible. That means the prime hiatul, the fundamental of the quasi-static is that it must be internal irreversible. It must be external. What is that? What is happening? We don't bother about that. So that work is, during that process the work will transfer, that is a boundary phenomena work, and these are the path function. It is not a state variable, and we calculate the integration P into dV, and P is the absolute pressure and P is the function of volume. Okay, now we will discuss again we discussed that flow work. That means the energy associated due to the pressure difference when the fluid is flowing. That means fluid will flow from one point to another point. There must be pressure gradient. Due to that pressure gradient, there must be a flow. Due to that flow, we associated the work. That means that work is not a boundary phenomena. This is the stored form. That means it is a system property. Okay. So one thing is very clear: work transfer and work change. That means in this condition the flow work will change, it is not transfer. Why? Because it is a property. But the boundary work will not change, it will transfer. That means the transfer term associated with the boundary phenomena, change term associated with the system phenomena, system property. When there is a system will change from system, when there is a system will change. We cannot say that when the system will transfer. No, system always change. That means what is the quantity associated with the system, that is your property. Okay, so like that we will discuss all the things. And the area under the curve, that means P and V axis, if you project the project the area on the volume axis, what is the area we will projected, that area is indirectly, it is gives the work transfer. Okay. So we will discuss all the we already discussed all the things. Now we will solve some problem. Now today we will solve again some few problems, so that we have to go through that more confidence. Okay, so what is that? See, so this problem will done. This problem already done. Okay, so this is the very important problem which currently asked in the GATE question examination. So it is very important. Okay, we will discuss also when we discuss the entropy chapter. Now this problem will also discuss where is the mistake. Okay, now next is this one also discuss this problem. What is the motive to take this problem? The motive to take this problem is to how to balance, how to draw the free body diagram of this piston. Okay, so now next problem is this one. This is your next problem. Okay, what is that? See, this is your a thick piston is initially held in a cylinder by a pin. My dear, see, if you want that the piston it is at that position, there are a few criteria. What is that? What is the criteria for that? That is, if you hold the piston as in that position, there are three criteria in general in thermodynamics. What is that? We installed a pin. That means if you put a pin connected between the cylinder wall and the piston, there must be a hold. That means it acts as a residue. It acts as a fixed volume. Number first. Number second way is that when the piston is touch on the stop, at that condition also there is a fixed volume, right? Also there is a fixed volume. So initially when we are taking the piston, it is as a pin or this piston is at a stop, both condition, if we increase the pressure, the volume is constant. That means at this point, see, if there is a pin is there, and now we increase the pressure inside the system. Though there is a pressure will increase, but volume doesn't increase. Okay, and and also if their piston will touch on the stop, so the pin it is act as a stop. Okay, so we'll discuss in this problem while solving the problem. Okay, so this is a okay. So okay, so a cylinder, this is a cylinder, there is a pin. Pin is a mechanical member shown. Assume that the cylinder contained a carbon dioxide. The cylinder in which the fluid is there, that is carbon dioxide, and have a pressure 220. Okay, and take ambient temperature, that means surrounding temperature is 300 Kelvin. That means if this is your system, we take a carbon dioxide as a system, outside is the surrounding, outside that surrounding property it is given 300 Kelvin. Okay, see the density of the piston it is given. Why the density of the piston is given? Why? Because we indirectly calculate the mass of the system, mass of the piston. Okay, this is your piston. This is your piston. How to calculate? Density is equal to mass by volume. Density is equal to mass of the piston divided by volume of the piston. Okay, volume of the piston. What is the piston volume? This length, that means horizontal length into the thickness, that means 100 cross 100. We can find here mass of the piston. Okay, no problem at all. Okay, assume atmospheric pressure, that means the atmospheric temperature also it is given, and atmospheric pressure it is also given. That means surrounding property it is given. Surrounding property is given. What is the surrounding property? Temperature is 300 Kelvin and pressure is 100 kilopascal. Okay, right. If the pin, now the point is very important. What is that? What is that, beta? If the pin is removed, see the beauty. If the pin is removed, at anyhow we eject the pin. At anyhow we eject the pin. If we eject the pin, what is happening? Think like that. First think. First your comment. What is that? If you read the, according to the given data of the question, inside pressure is high. Okay. Inside pressure is high, that is 200 kilopascal, and outside pressure is low, that means 100 kilopascal. There must be a pressure imbalance. That means inside pressure is high, outside pressure is low. If we eject the pin, it is obvious that the piston will move up. This is one point which is very clear. Okay, this is one point which is very clear. Is that, sir, if we eject the pin, piston will try to move up. Okay, piston will try to move up. Now, if the pin is removed, then the piston will move up. No problem at all. Now, assuming that after a while, that means during, after a while, the gas, this is very important, return to the ambient temperature. Return to the ambient temperature. That means if this is point number 1, the process is happening at temperature T1, the process is happening, the process again will return to its initial position, that means 2. That means according to the temperature property, the initial and final point is same. According to the temperature property. My dear, it is need not be the isothermal. That means initial and final are the property are same. It say that while the pin will eject, it will return to its initial temperature. That means initial temperature, T2 equal to T1, but it is not necessary that, see, if T1 is equal to T2, we cannot say that this is isothermal process. Why? Because end points are same. During the end point same, in between we don't know. Isothermal process, that means throughout the process 1 to 2 have the same temperature. So we cannot say that this process is isothermal. This is very clear. That means this T1 equal to T2, but we cannot say this is isothermal. Let's suppose beta, if we draw this, let's suppose this is your temperature axis and this is any axis x. Okay, initially the temperature is T1, finally the temperature is also T1. So this is the line of T1, this is T2, that means T1 equal to T2. It may be, see, it is not necessary that the cylinder is insulated. That means it is obvious, it's your common sense. At this point it is a state 1. Let's suppose this is state 1 at this temperature. Let's suppose, at this point we take, this is at state 1 at a temperature T1. When the piston will expand, piston is not expanding. When the piston is moved up, what is your observation inside the system? Either the temperature will drop or increase. See, this is a carbon dioxide, so we don't use that like that. If this is a very, so automatically if piston will move, the system, see, if there anything, if it will expand, it must be a drop in temperature. That means something you compress, it's in, not that you think like that, something is you compressed, its temperature is to be increased if there is no any heat transfer. Mind it, in general, if we compress the system, temperature will increase. If we expand the system, temperature will reduce. Nothing else. Okay. So at this point, now it will expand, the temperature will drop. So it may be like that, and finally it is reached at initial position. So it is like that position. This is 2. So see beta, initial and final point are same, but it is not necessary that in between all the temperature are same. See, this is vary. So it is not isothermal process. Think like that. Okay. Now, under these circumstances, whether the piston, that means the question is asking that whether the piston touch the stop or not. Touch the stop or not. This is your question. Okay. Touch the stop or not. Touch the stop or not. So go further. This is your piston, this is your cylinder, this is your piston, this is spin, this is your stops. No problem at all. Now, what is given here? Surrounding condition it is given. Yes or not? Surrounding condition it is given. What is that surrounding condition? We'll take T infinite is 300 Kelvin. Okay. And atmospheric pressure P infinite. This is infinite is nothing. This is a free stream condition. Outside condition is 100 kilopascal. Outside condition it is given. Now, see, we take state 1. Something, some large, so that you can visible very clearly. State 1. Okay, state 1, and this is state 2. Okay, state 2. No problem at all. What is the state 1? What is the question? State 1, the pressure it is given. What is that? 200 kilopascal. Sorry, 220. That is your 220. Okay, 20 kilopascal and density of the piston, it is given 8,000 kg per meter cube. Okay, what is the state 2? T2, this is for the system. This is for the system. T2 again reach as a T1 atmospheric temperature. That means, see, T2 will reach again to its, that means T2 is your atmospheric condition 300. Return to its atmospheric condition 300 Kelvin. Okay, return to its atmospheric condition. Now that means it is obvious that the temperature initially it must be 300. Now beta, I am asking one question. If it is like that data, that means initially the temperature is 300 Kelvin, and if it will expand, that means we have to find at this temperature, when the system is at this temperature, that means the same temperature, whether the piston will touch the stop or not. That means what is happening? How we maintain this temperature? That means, see beta, if piston will expand, how it is like that, if the piston will move up, it must be a temperature drop. It must be a temperature drop. So we'll maintain the final temperature, it is same, we supply the heat. It may be like that. Yeah, churning, anything is there. Okay, so this is final temperature of the system and this is initial temperature of the system. So from that one we can easily find, and this T1, that means T2 is equal to, this T2 is equal to, we like that, T2 is equal to T1, and thus T1 is equal to T infinite, and this is your 300 Kelvin. No problem at all. Okay, now, so here write but need not be constant throughout the process. Okay, need not be constant throughout the process. Okay, beta. Now, so we have to calculate something. We have to check while the system is at state 2, that means when it's returned to its temperature 100 Kelvin after ejecting, whether the piston will touch or not. That means we have to find, what is our question? The question is that, what is our question? Question is that whether the piston will touch the stop. This will ask him, okay? Whether the piston will touch the stop or not. This will ask him, okay? This is asking, okay? Now, for that one, add something. Now, okay, so see this one. If, see beta, my dear, if this is your, if this is your piston, see this one, if this is your piston, okay, we have to draw free body diagram. If this is your piston and the piston density it is given, that means mass it is given, that means weight, we can say that the weight it is given. So first, this is your system, in this side there is a system, in this side there is atmosphere. So on the piston beta, on the piston, this is your weight of the piston. Yes or not? This is your weight of the piston. Okay, this is your weight of the piston. Weight of the piston, which act as a CG from the CG, no problem at all. Inside, there is a gas pressure. Yes or not? This is your gas pressure. Gas, that means carbon dioxide. Outside, there is atmospheric pressure. Yes or not? Outside, there is atmospheric pressure. Yes or not? Yes or not? This is the free body diagram of the piston. Great, no problem at all. And this will find, what is Atul? Atul says that, sir, we consider equilibrium of the piston, but why? See, why? Because this is a quasi-static process. We assume that this is the thermodynamics process. See, you are asking that we consider the equilibrium position. Why the equilibrium position? Why? Because we have to find, see, what is the, this is not a static equilibrium. This is not a static equilibrium. In the static equilibrium, this is a static, but it is a thermodynamic equilibrium. That means delta P tends to 0. See, if we take a static equilibrium, or there is a thermodynamic equilibrium. So in a static equilibrium, delta P, that means sum of all the forces, if you take forces, and if thermodynamic equilibrium, delta P tends to 0. So it is free body diagram. We apply the static equilibrium. That means net force is equal to, and we have to find what is the internal pressure at that position. We have to find what is the internal pressure. That means what is the internal pressure, or you can say that what is the total external pressure at that position. So at that position, we can find any pressure. That means if this is your balance position, so what is the pressure inside the pressure? We have to find what is the inside pressure due to weight, due to atmospheric, due to the spring. Also there is a spring will mention. So there is a spring. So what is the pressure? And this see my dear, if you find this pressure, due to that pressure, the piston will expand, or expanding, the piston will move up or down with equilibrium. That means if you find the pressure in this one, this is P equilibrium. And this P equilibrium, it is your minimum pressure at which the piston will move. It is clear? It is clear? Okay. It is clear? So this is your concept, okay? Now, so we have to find, this is thermodynamic equilibrium, and this is your static equilibrium. Very important. Okay, now, so we have to find it. So beta, free body diagram, if you take a free body diagram, so this is your outside pressure P infinite into area. This is your inside pressure P into A. This is your mass of the piston into G. So if there is an equilibrium, net force, it is 0 in the y direction. That means if you find, that means PA is equal to P infinite A plus, this is force divided by, this is force. So mass of the piston into G. Now we have to find the pressure, that means P infinite plus mass of the piston into G divided by. My dear, this is your minimum pressure. Mind it. This is your, what is this pressure? What is this pressure? This is your equilibrium pressure. Very important. Pressure. This is equilibrium pressure, and there is a also called minimum pressure at which system will execute. This is very important. So this is the equilibrium pressure. So if we remove the stop, the piston will move up through this pressure. And through this minimum pressure, whether the piston will touch the stop or not, we are asking. The question is asking. Okay? Okay? So we'll take, so this is your, now how to calculate theta. So initially, if you think that, what is the volume, initial volume? That means state 1. State 1. What is the information is there? P1 is 220 kilopascal, it is given. Yes or not? No problem at all. So what is the volume? Initially V1. We know that pi by 4 d square into h. So we have to find, this is your d, this is your d, okay, and this is your h, initially h, 100. Okay, so put this value. So pi by 4 d you have 0.1 mm, that is mm it is given, h is 0.1, 100 into 100. So what is the value? This is value 0.785 into 10 to the power minus 3 meter cube. This is your initial volume V1. So we have initial pressure, we have initial volume, no problem at all. Okay, we have initial pressure, we have initial volume and initial pressure. Now we have to take a mass of the piston. Okay, what is the mass of the piston? Mass of the piston. What is the mass of the piston? What is the mass? Mass we have to calculate easily. Density into volume of the piston. Okay, put all this value. Density, it is 8000. Volume, piston pi by 4, very important, into diameter 100 mm, so 0.1 square, into piston ka thickness, that is also given 0.1. So this value, if you find this value, this is your 6.28 kg. So this is your mass of the piston. So initially we have to find, initially condition we have to find, and what is the mass of the piston we have to find. Now, this is your situation. Now, we eject the pin. So, in this condition, what is we say that after, what is that? After removal of pin, see how to check in each and every question you apply such type of concept. If any type of question they are asking that piston will touch the stop or not, initially you assume the piston will touch the stop. This is your criteria. You think like that. Initially, that means we assume, this is assumption. Yeah, take. We take. Why? Because we don't know whether it is touch or not. So if it is a touch, see my dear, if the piston will touch the stop, what is happening? What is happening? If the piston, if we remove the pin and piston will go up and it will touch the stop, what is happening? The system pressure will increase further at a constant volume. Yes or not? At a constant volume, the system pressure will increase. Why? Because it will touch the stop. That means the stopper doesn't allow to go further. So automatically the system pressure will increase. So we'll check that final condition, the pressure is still high as compared to atmospheric or not. If the pressure, see, if the piston will moving up, what is your thinking? If the pistons are moving up, the inside pressure will reduce. Reduce. At which pressure it will reduce? You may think that it is obviously 100. Why? Because outside, what is the outside condition? It is here. Outside condition 100. So if the piston will try to move, and at minimum pressure at which the stop, nearer by the stop, the system pressure will drop and 100. But while the piston will touch, you assume that the piston will touch the stop. While it is touching, still the inside pressure is high as compared to the atmosphere. You say that it must be touch the stop. Right. At which condition it cannot be touch the stop? Yes, obvious. We'll discuss this problem. This statement we will discuss. That means if the inside pressure is equal, that means very equal, less than. That means the system pressure will try to go up. And if the system pressure will touch the stop at that point, and at that point the system pressure is less than the atmospheric pressure, then it not means that the stop will touch the piston. I repeat. See, I repeat, there are two situations. Either piston will touch the stop or not. See, if the piston will touch the stop, automatically when it is touched, when the inner pressure is still higher than the outer pressure. That means if you calculate at state point 2, if the state point 2, the pressure is still higher than the atmospheric pressure, piston will touch the stop. Now, if the piston doesn't touch the stop, that means the final condition is lower than the atmospheric condition. So it is not able to move up or touch. It is clear? Atul, it is clear? Clear? Yeah, anything you want? I will discuss again. Okay, so after removal the pin, if the piston touches the stop, it would travel at a distance. How much it will travel? At a distance of how much? 0.05 meter. See, it will travel. This is our piston, so it will, if we touch the stop, it will travel this distance. It is visible. It will travel this distance. 0.5. Okay, the distance is clear. Now, next. That means, what is the final state? That means, state 2. What is the state 2? We have a T2. And what is the T2? Is equal to T1. And what is T1? T infinite. This we have. Now, at state 2, what is the volume V2 of the piston, of the system? What is the V2? Same idea. See, this is 100, this is also 100, this is also 100, and this is 50. Okay, like that. Okay, so What is V2? Pi by 4. What is diameter? This diameter is 100 mm. All are in mm, so 0.1 square into distance. At where the student get mistake. What is the distance h? It will travel how much distance? Only this distance it will travel. You cannot include this 150. No, this distance you cannot travel. This is always there. So how much it will travel? This distance. This distance is travel. Okay. So this is your 0.5 whole square. No, not a square. So this is what V2 is 1.18 cross 10 to the power minus 3 meter cube. See the beauty. See the beauty. What is V1? We have a V1 is equal to 0.7585 into 10 to the power minus 3 meter cube. See the beauty. What is the volume condition? This is V2. This is V2. That means volume will increase. Yes. That means it will move. Volume will increase. It will move. Volume will increase. So V2 is must be greater. So accordingly you can check the answer also, whether you are correct or not. If anyhow, if the volume is less than this one, your answer is wrong. That means your process is wrong. You are doing a wrong way. Okay. Now, what is that? Initial temperature and final temperature are same. So, P1 V1 is equal to P2 V2. Same temperature. Okay. So, what is P2? Final pressure. This is very important. Why? Because we have to check what is the final condition of the pressure. So, what is the P2? P2 is P1 V1 by P1 V1 by V2. Put all this value. P1 you have 220. V1 you have 0.785. 10 to the 10 to the cancel out. That's why we are not right here. 1.18. Okay. So what is this value? This value it is your 146.4 kilopascal. Now beta, now the discussion will start. Now at this point the discussion will start. I think it is not visible, no problem. See. That means, see, very important, I am telling you. At that point, this is your piston cylinder, okay, and the piston will touch the stop, okay. Let's suppose this is your piston and it will touch the stop. This is our stop, okay. This is our stop. This is our one stop, touch, and this is your second stop. This will touch, okay. So this is your stops. Why? Because we assume that it will touch. So beta, it will touch, okay. So if it will touch, so at this, that means this is state 2. So what is the state 2? State 2, what is that? Our V2, we can write V2, it is your, how much? V2, 1.18 cross 10 to the power minus 3 meter cube. P2, it is your 146.4 kilopascal. T2 is again 300. So we have all these things at state 2. At state 2 we have. Now my dear, you focus this. Okay, this P2. So this is pressure is what? This pressure P2 exerted by the piston on the system. Piston include its atmosphere. That means this is the pressure exerted. Why? Because it will displace the atmospheric pressure. So atmospheric pressure, and also it will maintain the weight of the body piston. During that it will reach that this pressure. That means this pressure is the pressure exerted by the piston plus atmosphere. That means, yeah, exerted by the gas on the piston. You may say that like that. That means you may say like that, sir, this is the pressure exerted by the gas on the okay, no problem, we'll don't write on the piston surrounding, yeah, anything, it is okay, no problem, by the gas. This is okay, this is okay. Now by the gas obviously on the piston. If you write that right, on the piston, no problem at all, okay, no problem. Now that means, what is P1 beta? What your P1 value? It is 220 kilopascal. So someone ask you, first question, someone ask you, there are two type of question will form, whether the piston will, if the pin will ejecting, whether the piston will move or not. So it must be move. Why? Because P2 reduce. Yes, when the piston will move up, the system pressure will reduce. That means here one observation is that, what is that? P2 is less than P1. What is mean? This means that it is not that it not means that piston will touch the stop. No, it is not mean like that. This is very important. This means that, sir, piston must be move up. Now, once the piston will move up, whether it will touch the stop or not, we'll calculate. So, if we do that, what is the external pressure on the gas by the piston? That means P external on the gas by the piston. What is that? This is your P infinite plus mass of the piston into G divided by A. Yes or not? Yeah, P external, this you have to already calculate. So, what is P infinite? 100 plus mass of the piston 6.28, G 9.81 divided by area pi by 4, D 0.1 gas square. If you calculate, this is your 107.844 kilopascal. Now, think like this. See beta, very important. That means, very important, when the piston will touch the stop, we assume like that, this is the pressure at which the piston will touch the stop. So this pressure 146 and this pressure is what? The pressure exerted on the gas by the piston. That means this must be external pressure. See, the external pressure is less than the internal pressure. That means internal pressure is higher than the external pressure. That means while it will touch the, when it is touch the stop, still the pressure inside the gas, still the pressure inside the gas, that means inside the piston cylinder, still inside the cylinder, the pressure is higher than the external pressure. That means it must be touch the stop. If this pressure is higher than this pressure, if this pressure is higher than this pressure, that means piston doesn't touch the stop. This is very clear. That means external pressure, that means this is a resistance pressure. This is what? Resistance. Resistance pressure. That means the resistance pressure is lower than the system pressure. That means system pressure are able to touch the stop. That means if we write like that, so P external by the piston on the gas. This is how much? This is your 107.484 kilopascal, and P2, this is at which when piston touch the stop. At this condition, what is the pressure? 146.4 kilopascal. Okay. That means P2 is still higher than the P external pressure. That means must be touch the stops. Note, if P2, that means if external pressure is higher than system pressure, in that condition piston not able to touch the stop. Clear? Clear? This is clear? Okay? Now, so we'll take a next problem. This is the next problem. This is a very simple problem. This is GATE 2020. Okay, current year, little bit current. The 2000 previous classes we are already discuss that 2023 problem. Now we will discuss 2020 problem. See, this is very simple problem. What is that? See that, but there is a, see what is why we are taking this problem? Why we are taking this problem? Why? Because you cannot draw, you are not able to draw the PV diagram of this system. See, if you try to solve any problem associated with the work transfer or heat transfer, try to draw the PV diagram or TS diagram so that it becomes a very clear. Now, what is the, see, this is same, this is the stopper. Now, at this time, this is a stops. At this time, so beta, at that point, there must be a, what is that? This question is what? There must be a pin is there. There must be a pin is there here. There must be a pin, yes or not? Here there must be a pin. But now in this time, they are freely rest on the stop. What does it mean that? Why it is freely? Why it is here? First think the figure. First observe the figure. What is the figure is there? There is a piston, a cylinder. There is a piston. That means weight is there. There is a stop. There is a spring. And the piston is at a floating condition. These are the floating condition. Okay. The piston is in floating condition. Okay. So when it will float. When it will float, that means beta, the internal pressure must be external pressure. At that condition, it will float. Now, when it start to move, you supply energy from the surrounding. Either you churning the gas or air, or either you supply a heat. Okay, yeah, resistance, any mechanism, so that this system will energize and piston will try to move up. This is second point. Number third, you continuously supply the heat, the piston will continuously moving up, and there may be a chance that the piston will try to compress the spring and it will finally stop by the stoppers. So, my dear, it is very clear. This is state 1. This is very important. This is the state 1. What is the genuine diagram? This is very clear, I am telling you, beta. This is very clear, I am telling you. See, what is the genuine diagram? Okay, see this one. If you draw the PV diagram, beta, see this one. If you draw the PV diagram, why it is yellow? If you draw the PV diagram, okay, this is your pressure and this is your volume diagram, okay. See this one, very important. Now, this is your pressure axis and this is your volume axis. Okay. What is your observation? Sir, this is our system. Air as a system. Now, when the piston is floating, very important. When the piston is floating, that is the initial point. That means we have, at this point, we have a pressure and volume, let's suppose. This is point number 1. Okay, P1 and V1. Now, you supply heat. If you supply a heat, piston will try to move up. Piston will try to move up. But there is constant resistance force, yes or not? There is a constant resistance. That means piston will try to move at equilibrium condition. Why? Because you continuously supply the heat, piston will try to move continuously at equilibrium position, at equilibrium condition. Up to what? Up to this point. Up to this point, piston will travel. That means this point to this point, the piston will travel at equilibrium pressure. And that equilibrium pressure is constant. Why? Why? Because external resistance is fixed. That means resistance is fixed. Resistance is fixed. See, no resistance. That means, resistance is there, but there is no any change up to this point. That means up to just touch the spring, there is no any change in resistance. So from point 1 to point 2 dash, when it will just touch the stop, the pressure is constant. That means this point, let's suppose this point 2, this is your 2 dash. This pressure is an equilibrium pressure. And it is a constant. Okay. Now in general, this is the linear spring. This is the linear spring. For the linear spring, see here, it is given that considering the air inside the cylinder is a system and working. Heat is now added and the piston is moved slowly. This is very slowly. That means quasi-static process. From the initial position until the reach the stops. That means we have to finally go at the stops. The spring is constant. The spring constant of the linear spring. This is a linear spring. Where it is the linear spring? You just think that the change in pressure is directly proportional to change in volume. This is very clear. Okay. So this is a linear. So from here to here. Why? Because when it will come touch and after you continuously supply the heat, the piston will try to compress the spring, and while the compression, resistance will vary. That means when it will try to compress, the spring will try to exert more and more force. That means resistance is vary according to the volume. That means volume will vary, pressure will also vary. That means if it will compress, try to compress, the space will increase inside the cylinder, and also the resistance will increase. So pressure also will increase. So this point 1, this is a initial point 1, and at the point 2, what is that? V of the spring. This is the V of the spring. That means just touch. Volume of the touch. That means this is a spring. And this volume is a stops. That means at the stoppers. Piston will reach at the stops. That means this is a V stop. This is a P stop. Okay, this is a volume diagram, pressure volume diagram. This is a pressure volume diagram. You cannot find anywhere this diagram. In your anywhere you have resource, you cannot find this diagram. Okay, but why you cannot find it? Why? Because many of the teachers will try to solve without drawing the diagram automatically, but there may be a mistake. This is a simple question, so without drawing you can solve, but without drawing this question, if there is a complex question, there must be a mistake. I will discuss in next classes. If you not draw the PV diagram, jai khatam, kharas, finish. Okay, so what is that? So they are asking that work interaction to the nearest work interaction. So this is your work interaction total. This is your work interaction. So my dear, work interaction W net. This is work net is equal to W 1 to 2 dash plus W 2 dash U. This is 3. 2 dash to 2. So 1 to 2 dash, the process is equilibrium constant pressure, and 2 dash to 2, there must be a linear. So if you find the work, simply you find the area, this area plus this area, this area plus this area is what? This area. So if you find the area, you have to find the stop volume. Also you find the stop volume. Okay, so this is our next target. So we have to find it, no problem. So from 1 to 2 and 2 to 1, okay. So from okay, let's see, for an initial expansion, first initial expansion. Initial expansion, that means system will just touch the spring, okay, of 8 centimeter. Yes or not? That means what is the process? 1 to 2 dash. This is what? Piston just touch the spring. Touch the spring. That means, and this is the process is very slow. That means 1 to 1 dash is equal to integration P dV. And P is what? P equilibrium, and this is constant. Okay, so keep outside from the integration. Into process, this is 1 to 2 dash. That means V2 dash minus V1. Okay, so what is the pressure at that point? Equilibrium. So this equilibrium pressure is nothing, it is P1, okay, initial pressure. And the initial pressure it is given. How much it is given? And the initial pressure of the air inside the cylinder is 105 kilopascal, okay. So this is your 105 cross 10 to the power 3 Pascal. Final volume it is given. Yes, V2 dash from here. Okay. So what is that? Area into displacement. Yes or not? Matlab, the area. What is the area? What is the volume? Area into displacement. So what is the area? Area it is given or not? Yes, area of the piston. It is given 300 centimeter square. Area into what is the displacement? 8. Okay. So area this is given. Piston area it is given, and displacement it is given. So this is your volume. So this is your area into displacement. Area of piston into displacement. Yes or not? So if you put 105 cross 10 to the power 3, what is the area of the piston? 300 cross 10 to the power minus 4 into what is the displacement? 8 cross 10 to the power minus 2. If you solve this one, this is your 252 joule. Okay, 252 joule. Now, this is 1 to 2 dash. Now, there is important. So, 1 to 2 dash, we have to find the work. Now, we have to find the work 2 to 2 dash. 2 dash to 2. Okay. So, after touching the spring, work done to compress the spring. Compress the spring. That means we have to find what is the work will require to compress the string after the touching. Why? Because 1 to 2 dash, 2 dash to 2. So 1 to 2 dash there is a expansion equilibrium, but 2 dash to 2 there is a compression of the spring. So What is the process? 2 dash to 2. So what is that? Work. What is the spring work? Everyone, half change in potential energy, yes or not? That means change in potential energy of the spring. Very important. And what is the potential energy? Half spring constant x square. X is what beta? Compression of the spring. Yeah, displacement of the spring. Displacement of spring. Yeah, compression of the spring. Okay. So what is that? Half K, it is given 112.5 into how much it will be compressed? It will compress up to stops. So up to a stop, what is the distance? Again 8 centimeter. So this is your 80 square. So if you calculate this one, so finally it is 40 joule. If you calculate, this is 40 joule. So initially there is a 252. So total work W is equal to W1 to 2 dash plus W2 dash to 2. So this is your 252 plus 40. So this is your 292 joule. 292 joule. It is clear? There any problem? So this is your type of spring. That means spring will compress, spring. There is also in which, see, if the problem, there is a churnering. Okay, like that the question will ask. So better to try. What will take? Will better to see if you done the pressure this line, that means area. If you find this area, you have to find the volume. So better we are going to the spring formula. Pressure is potential energy. Otherwise, if you find the area of this one, this area will easily find. But stop. So you have to find the stop area. So this is your like a triangle. If there is a two, one is a rectangle, other is triangle. So add this to one, then you have. So it is little bit lengthy. So easily if you have to apply the potential energy concept of the spring, and we get the final answer. Okay. Now it is clear, everyone, please. Now it is clear, everyone, please. So if it is clear, then we go to the first law of thermodynamics. Okay. Yes. Before that, we study the concept of energy. What is the concept of energy? First, we will discuss concept of energy. Okay. Discuss concept of energy. Okay. Concept of energy. So in the thermodynamics, if you say that energy this is our energy. So beta, think that before going to the first law of thermodynamics, we study the energy. So according to the thermodynamics, there are two types of energy. One is the energy is stored. That means these have a two nature. First is change. Second is transfer. Second is transfer. If we take change, there must be a property. And if we take a transfer, there must be a boundary phenomenon. Okay. If this is your property, then this is your point function. Function or state variable. If this is a boundary phenomena, it is a path function. Right. That is called energy of the system. This is called energy of the system. This is called energy of the system. One is the system. That means this is called total energy of the system. Of the system. That means, example, internal energy. This is your internal energy denoted by capital E. Okay. Now, transfer, that means not a energy of a system. This is called, that means it is transfer mechanism. That means it should cross the boundary. That means if this is your system, if this is our system and system have a total energy E. If this is your system have a total energy E. Now, this system energy will change, not transfer. This system energy will change when there must be something in and something out, या only in, या only out. The in general, we take work, and out we take heat. No, sorry. In we take heat, out we take work. Okay. That means transfer, it is example, this transfer example is work and heat. Work and heat. So, during the transfer of this energy, this energy, the system energy may be increased, may be decreased, or remains constant. That means, if you add the energy in the form of heat through this boundary, let's suppose this dq, yeah, q, let's suppose this is dq, this is dw, let's suppose. So this is a boundary over which this will transfer, and this is a boundary over which this work will transfer. This is a boundary phenomenon across which it was dq is the energy, heat energy, which is transferred across this boundary through the temperature difference or any gradient. So if we add something and if we reject something, so what is the property of the system, energy form of the property of the system, may be increase, may be decrease, or remains constant. That means if this magnitude is higher, that means you are removing higher energy as compared to the input, the system energy will reduce. If you add more energy as compared to removal, the system energy will increase. Okay? If we are not any interaction of the work and heat, the system energy will remain constant. So that this energy, this energy, that means total energy, that means internal energy, may be increase, may be decrease, or remain constant. The change is zero. That means this change have a three type: increase, decrease, or zero. Zero. Increase, decrease, or increase, decrease, or zero. This will increase, this will decrease, or zero. That means this is a system property. Okay, so we'll discuss this type of energy, and we'll discuss very regressive manner and very heavy dose. I will give you next session very heavy dose, and we have to come with some conclusion, and that conclusion is a property. Okay, so we'll discuss next session. Okay, up to that, thank you, bye bye.